We've spent time now on looking at atoms, so let's talk about what happens if we change an atom by taking or giving extra electrons to the atom. We can't normally, well, it's a lot easier to do that than it is to add something to the nucleus. So let's concentrate on how we form ions and what goes on. You can actually see in the diagram I've put on the front here how the fact we've changed a magnesium atom into a magnesium ion. I've included both possibilities. Then we'd simply need to think about which one would be energetically easiest. Would it be easiest to gain 6 or lose 2? And I think that's rather obvious that losing 2 is the option. So if I've got 2 less electrons, I form the magnesium 2+ ion. An important thing to remember is that because the number of protons and electrons are the same in an atom, the atom is uncharged. If we have an imbalance between protons and electrons, we will actually form a thing called an ion. We've already seen that if we have an imbalance between protons and neutrons, or a different number of neutrons in an atom, we form an isotope. So there's something slightly new to learn. As I mentioned before, everything looks for the easiest option. And so if it's going to be gain or lose electrons, we tend to find that the atom will, you choose the easiest option, choose in inverted commas of course, that personifies the atom, which is not quite correct, but it will tend to do the energetically easiest option. If it's energetically easiest to gain electrons, it will have more electrons than protons, so it will be a negatively charged ion or an anion. If it is easier for the atom to lose electrons, then it will have more protons than electrons, which will give it a net positive charge, and it will form a cation. Now don't forget that all these electrons being lost or gained occur in the valence shell, and we tend to think about it in terms of the octet rule, filling up the magic number of 8, which corresponds to the same electrons as we find in inert or noble gases, our group 18 elements. And this explains why they are inert. So we actually say that ions tend to be isoelectronic, which means they have the same electron configuration as an inert or noble gas. If we consider the basics that go on, we know that opposites attract, and this is the basic rule of electrostatics. If we've got opposite charges on things, they will be attracted to each other. If we've got the same charges, they will be repelled. Now, obviously, in an atom, we've got a positive nucleus, thanks to the ideas of Rutherford, and negative electrons, thanks to the ideas of Thomson. And so we see these two things being held loosely or being attracted to each other. And then, of course, we would have repulsion between the electrons. And this is important when we consider other things. For example, if my valence shell is the third shell from the nucleus, in other words, the valence shell is where we find the outermost electrons. So if it's a third from there, then all of the 2 layers inside are going to be pushing against or repelling the valence electrons, and that makes it easier for them to be removed, and this is something we need to think about when we are talking about ions and ion formation. The measurement of how easy it is to remove an electron from an atom is referred to as the first ionization energy. And this is normally measured in units of kilojoules per mole, and you can find the values for the elements on, I think it's table number 7 or number 8 in your data booklet. It actually gives other information about electrons on that table as well, but more about that later. The equation I've shown here from the element X, now it doesn't matter whether X is a metal or a non-metal, where it is, the same rules apply. So we're going to change the X atom into the X1 plus ion and release one electron. Notice that we have the subscript G, so we're assuming and we're saying that all these things are occurring in the gaseous phase, and that becomes important. So one of the questions you might find in paper 2 could be define the term first ionisation energy. And so we can consider it in two ways. We can consider it in terms of individual atoms, or as we'll find out, we can consider it in terms of moles. So if we're talking about atoms, we are talking about the amount of energy required to remove an electron from a single gaseous atom. Note, gaseous must be emphasised in this. Don't leave it out. Now, your IB exam will have multiple definition questions. This could be one of them, so it's very, very handy if we remember this definition. However, if we think of it in terms of moles, our definition changes ever so slightly to the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Either of those definitions would get you the mark for that question. So remember one of them. If I was going to give preference to one, I would possibly do the moles one, because as I've said to you, by definition, first ionisation energy is given in units of kilojoules per mole. Now, relating this back to that wonderful thing called the periodic table, we see that there are some trends or patterns existing in the periodic table, and the ionisation energy, or the first ionisation energy, tends to increase across a period. And I've said here it's due to effective nuclear charge, which means that across a period, the electrons are in the same orbital or in the same shell, but as we go from one to the other across the period, we increase the positive charge in the nucleus by 1. So won't that affect our electrostatic attraction? Wouldn't there be a greater attraction between those electrons, valence electrons, and the nucleus? And wouldn't that require more energy to remove those valence electrons? I think the answer to all those is yes. If we then consider what it's like going down a group, we actually find it decreases. And it decreases because as we go down the group, we add one more layer of electrons, or one more shell of electrons. And this means we're going to have shielding effect, and the inner orbitals or shells of electrons are going to try to repel the valence shells. So that makes them easier to remove. So it requires less energy to remove them, and our IE, ionisation energy, decreases. I hope that's clearer. More about ions and other things later.